Hello viewers, welcome to Exploring Technologies. In this video, I'm going to explain the basics of the transform. So I will cover following topics. First, I will explain what is a vector in a product. Then I will explain about the orthogonal vectors. Then we will see what are the orthogonal and orthonormal basis functions. Then I will explain the bi-orthogonal and bi-orthonormal basis functions. Then we will see how the transforms are created, evolution of the transform with help of the transformation matrix with orthogonal basis functions. Then we will see how we can transform one-dimensional and two-dimensional data using real and complex orthogonal transforms. Then we will see the bi-orthogonal transforms also. And in the last, I will explain the numerical examples to make you understand the concepts. And then we will see the some popular transforms and their corresponding transformation matrices. So let me start this video. First, let me show you what is a vector inner product. So just consider the two vectors u and v in n-dimensional space. Let's say the u vector is defined as u1, u2 and un. And vector v is defined as v1, v2, vn. So the inner product of these two vectors is defined by this operator. Okay, so u transpose into v. So because of the u transpose, the column matrix will become the row matrix. So one row multiplied with the one column. So that is actually equivalent to the element to element multiplication. So you can see the first element of u is multiplied with the first element of v, like that. Or mathematically you can write sigma ui vi I1 to n. So that is also known as the dot product in mathematics. Okay. So now let's consider if your vectors u and v are complex vectors, then how the inner product will take place. Then inner product of these two complex vectors will be defined by this equation. So here first you take the complex conjugate of the u, then you will transpose it and then multiply with the elements of the v. So this you can see here. So each element of u is first we get the complex conjugate of those elements and then simply multiplication, element to element multiplication. I'm the complex conjugate of first element multiplied with the first element of v, second element of u, complex conjugate of that and multiplied with the second element of the v vector. So similarly you will do this for all n elements, or mathematically you can write I equal to 1 to n ui star vi. Star means complex conjugate. So now these two cases I have taken the discrete vectors. So if your vectors are continuous functions of time, like one is a ut and another is a vt, let's say both are defined in the interval a and b, then the inner product of these two continuous functions can be expressed by this integration. So integration in this limit a to b, multiplication of these two vectors ut and vt. Okay, so if these functions are complex functions, so again you will take the complex conjugate of the u multiplied with v and then taking integration from a to v. Now we have some axioms, like if I have the real vectors, then u v inner product is same as v u. Okay, this is known as a commutative property, but this is not true for the complex vectors, because if u and v are complex vectors, then uv inner product is not equal to vu. In fact, it is vu and then complex conjugate of total, right? The second property is the distributive. So if two vectors are added and then resultant is having inner product with the third one, then you can separate them in these two pairs. So u inner product w and v inner product with w, right? So this is distributive, and this is associative. So one vector u is having multiplication with some scalar, let's say. So alpha u having inner product with v, that is same as inner product of u and v, and then total is multiplied with alpha, right? And the last one is that when you do the self inner product, I mean u having inner product with itself, then obviously it will have some non-zero value, right? But if u having inner product equal to 0, this is only and only possible when u itself is 0, otherwise it is not possible. So these are few properties of the inner product. And now let's see some examples so we can understand this concept better. So just consider these two vectors u and v in a three-dimensional space. Okay, so their inner product is uv or vu because these two are reals. So that is simply the element to element multiplication. That means 4 is multiplied with the 2, minus 1 is multiplied with the minus 2, 2 is multiplied with minus 1, right? And then summing all these, so you have 8 plus 2 minus 2, that is equal to 8. So the inner product of these two vectors is 8. Now consider the case of the complex vectors. So let's say u is this complex vector, 1 plus j, 1 minus j, minus 1 plus j, minus 1 minus j, and v having also the 4 elements. So their inner product by the definition is u star transpose v. That means we have to take the complex conjugates of each element of u, right? And then multiplied with the v vector. So 1 plus j is now 1 minus j multiplied with 3 minus 4j, right? 1 minus j is now 1 plus j multiplied with 6 minus 2j. Minus 1 plus j is minus 1 minus j multiplied with 1 plus 2j, like that. So it means the complex conjugate of u is multiplied with a v. So by solving this, we get 1 minus 5j. So that is the treatment for complex vectors. Obviously, as I have already said, that for complex vectors, the uv inner product is not equal to vu. In fact, it is equal to the vu star, means complex conjugate of the total outcome. Now let's see what is vector norm. Actually, vector norm represents the magnitude or length of the vector. It is defined in terms of the inner product by this operation. So these two vertical lines are actually representing the vector norm. So vector norm of the u is actually the square root of its self inner product, u and u. So just consider a vector u in three-dimensional space a, b, c having the elements a, b, c. Then the its self inner product will be a into a, b into b, and c into c. I mean element to element multiplication, first with first, second with second, and third with third. So this is a square plus b square plus c square. So having the norm by this equation, so that is a square root a square plus b square plus c square. So that is how you can get the magnitude of the vector in an n-dimensional space. You can also get the angle between the two vectors u and v by this formula. So that is cos inverse. You have to do the vector inner product, then divided by their individual norms. Okay, so that is the theta. Now let's see what are the orthogonal vectors. So we have just seen the formula of the getting angle between the two vectors. So suppose we have the two vectors w1 and w2. If the angle between them is 90 degree, I mean they are perpendicular with each other, then these two vectors are called orthogonal vectors, right? So this leads to actually the inner product of these two vectors equal to 0. So you can say that angle between the two vectors is 90, or you can say that inner product of two vector when equal to 0, they are called as orthogonal vectors. So just for these two vectors, their inner product is 0, or if they are continuous functions, this is the inner product which we have already defined, integration in the limit a to b. When this is equal to 0, they will be called as orthogonal vectors. So just consider this example to understand this concept. So I have the two vectors, one is 1 1, second is 1 minus 1. These are orthogonal because their inner product is equal to 0. Similarly, for as a continuous functions, we have sin omega t and cos omega t. If you do this operation, you will get 0. So these two are orthogonal vectors. So now let's see orthogonal and orthonormal basis functions. What are those? So we have just seen what is orthogonality. Now consider a set of n vectors like w1, w2, w3 and wn. These all vectors are orthogonal with each other. That means their inner product will be 0. So like when you have inner product of w1 and w2, you will get 0. You have w1 and w3, 0. w2, w3, any combinations when you try, you will get 0. So that's why mathematically I have defined the inner product wk, wl equal to 0 when k is not equal to l. That means not the self inner product. So what will happen for the self? I mean when w1 having inner product with itself. So that means when k equal to l, this is obviously will not be equal to 0. That we have already seen that axioms. Alright, so it will be some non-zero element. So these vectors are known as orthogonal basis functions. So all these set members of this set are known as orthogonal basis functions, right? They are also known as a span. So now assuming again that all these are orthogonal with each other, but if the self inner product is equal to 1, I mean for the same set, then these members are known as the orthonormal basis functions. So that is the difference. Now let's see what is the bi-orthogonality and bi-orthonormality. So we'll consider here for bi-orthogonal and bi-orthonormal basis functions. So for this, now consider the actually two sets of such vectors. So this is the one set and this is the second set. Having n number of elements, I mean vectors, and these vectors are actually mutually orthogonal. That means w1 is orthogonal with w2, w1 is orthogonal with w3, w4 orthogonal with w3, I mean any pair, right? So wk tilde, that is one element from this set is orthogonal with one member from this first set. So their inner product is 0. But when k equal to l, it means when the first element of first set having inner product with the first element of second set, then it is not equal to 0. Okay, it may be some other non-zero number. So if these two conditions are satisfied, then we call them as bi-orthogonal basis functions. Okay. Now if the first condition is as it is, but the second condition now changes. So instead of some non-zero element, if I get 1, that means 1, the first member of first set when having inner product with the first member of the second set, if they have inner product equal to 1, then this is known as the bi-orthonormal basis functions, right? So that is the basic difference. So now let's see the role of these basis functions. Actually, what is the importance of these basis functions? So from this slide, now the transform basics we will study, and we will see that how the transforms are evolved. So that is actually the basics for all popular transforms like Fourier transform, cosine transform, sine transforms, and wavelet transform, etc. Okay. So these basis functions are actually the main building blocks of any transform, such as Fourier, cosine, and wavelet. So let's consider a set of orthogonal basis functions as the set represented by W having some orthogonal members in the inner product space V. Then any vector Z, any vector in that space can be expressed as linear combinations of these basis functions as. Okay, so any vector Z can be expressed in form of these orthonormal basis functions as a linear combination. So alpha, all alphas are actually the coefficients, while W's are your orthonormal basis functions. Okay, so depending on the Z, this linear combination can be finite and can extend till infinity. Okay, so now let this vector Z has inner product with any orthogonal member basis function, I mean in which it is defined. Then let's say this Z having inner product with any member of its own orthogonal family. Then we will write obviously like this, because Z is alpha 1 W1 plus alpha 2 W2 like that. So inner product will be with each term. So we'll get these each terms. Just consider the previous equation where I have written Z equal to alpha 1 W1, then alpha 2 W2 like that. So this is having inner product with some member Wi, that is orthogonal member. So obviously it will have inner product with each element like this. Okay, so alphas are coefficients, so you can take out alpha. So now you have inner product of these orthogonal vectors, right? So as we know that W1 is orthogonal with Wi, so its inner product will be 0. W2 is obviously orthogonal with Wi, so its inner product is 0. So all inner products will be 0 except this. Here Wi is having inner product with itself. So in the definition we have said that if W1, W2 are orthogonal, then this will be some real number. If they are orthonormal, then this will equal to 1. Okay, so all terms will be zeroed out, only this term will remain. So that is equal to alpha I, Wi inner product. So from here I can find alpha I. So I can find ith coefficient of this linear combination by this operation. Okay, so as I have already said, if vectors are orthonormal, then this self inner product will be equal to 1. Okay, and in that case alpha I will be simply inner product of Z and Wi. So by this way we can find alphas. Now let's see how the transformation matrix can be formed. And this is the transformation matrix, which is you can say that is the extract of all the transforms, all the linear transforms, right? So your all very complex looking transforms can be considered as a very simple mathematical exercise of multiplying the two matrices. So let's see how it is possible. So we can construct a transformation matrix T with all these orthonormal basis functions, maybe either real or complex. So let me have the two orthonormal basis functions W1 and W2, right? So I'm considering just these two vectors W1 and W2 in two-dimensional space. That's why their length is 2 by 1 and 2 by 1, AB and CD. So just by concatenating these two, I can make a transformation matrix like this. So just keep them side by side. So AB, CD, AB, CD. So this matrix is known as a transformation matrix or kernel. And here, as I said, these W1 and W2 are orthonormal. That means their inner product is 0 and the self inner product is equal to 1 because they are orthonormal. This transformation matrix satisfies following conditions. If these vectors W1 and W2 are real basis functions, then T into T transpose equal to unit matrix, and the inverse of T matrix is equal to the transpose of itself. And if your vectors are complex, I mean W1 and W2 are complex vectors, so this becomes T into conjugate transpose, okay? And here the inverse of the T matrix is equal to the conjugate transpose. So now let's see how a one-dimensional orthogonal transform is achieved. That means if you have a one-dimensional signal, then how you can transform that signal into the another domain. So just consider a one-dimensional signal x whose length is n by 1. So it's a column matrix having n number of elements because it is defined in n-dimensional space. To transform this signal, you need transformation matrix T of size n by n. That is a required condition, okay? So this transform can be obtained by this equation. So this is your column matrix n by 1, and this is your n by n transformation matrix. So X is also your n by 1 matrix. So this is your, you can say it is your time domain data, and this is your frequency domain data. So you can see you can convert your time domain signal into the frequency domain just by having the matrix multiplication. So, and the inverse transform, that means if you want to find X again, obviously you just take T to the left side. So that will be the T inverse. So X equal to T inverse X, but we have seen that this transformation matrix having the properties T inverse equal to its T transpose. Okay, for for real vectors, for real basis functions. So this is known as orthogonal transform, and if your T matrix is made with the complex orthonormal basis functions, then equation 2 becomes this, okay? So equation 1 will remain same, but equation 2 will change. So T transpose will become T conjugate transpose, okay? So that is your one-dimensional transform. Later with numerical examples, I will show it to you that how you can perform on some examples, numerical examples. And now let's see the two-dimensional orthogonal transform. So consider a two-dimensional signal f that can be an image segment of size n by n. So to transform this signal, the transformation matrix will also be of size n by n. So this two-dimensional transform can be given by this equation. So this is your spatial domain. Let's say it's an image segment, then spatial domain signal is transformed into the frequency domain with this operation. So this is T, your transformation matrix, multiplied with your signal, and then T transpose. Okay, and the inverse transform. So to recover back your signal F, this operation is required. That is T transpose F and T. Okay, so this is orthogonal transform in two dimension. And if basis functions are complex, then your transformation matrix T is also complex. So the equation 1 will remain same, while equation 2 will change, and that will be this F, instead of T transpose, it will be the conjugate transpose, and this T will become the complex conjugate of the T. Okay, so the inverse transform equation will be changed. And now let's see bi-orthogonal transform. So for bi-orthogonal transform, actually we need two transformation matrices instead of one. So the one will be used for forward transform and other will be used for inverse transform. So now let us consider these two matrices as T1 and T2. So the forward transform will be given by this. I mean instead of the same T, the two different transformation matrices are used here. So we will use T1 for decomposition, I mean forward transform, and we will use T2 for inverse transform. So T2 transpose. Okay, so if your signal is two-dimensional, then the forward transform equation will be like this. I mean T1 for forward transform, and for inverse transform you will use T2, another transformation matrix. And if your T matrix is complex matrix, which is made with the complex orthonormal basis functions, then equation 2 and 4 will be changed only. So instead of 2 transpose, T2 transpose, that will be the T2 conjugate transpose, right? And here in equation 4, this T2 transpose will be the T2 conjugate transpose, and this T2 will be the T2 complex conjugate. So equation 2 and 4, I mean the inverse transform equations will be changed in case of complex basis functions. So now let's see the examples by which we can understand this concept better. So now consider the two real orthonormal basis functions W1 and W2. So W1 is defined like this: 1 upon 2 square root 2 1 1 1 upon square root 2 1 minus 1. So with help of these two basis functions, I can construct my transformation matrix T as, which I have already discussed, just keeping them side by side. I mean simple concatenation. So 1 upon square root 2 1 1, that is your W1, and this is W2. So this is your 2 by 2 transformation matrix. And here we can see that both W1 and W2 are orthogonal with each other because their inner product is 0 and their self inner product is equal to 1. I mean for W1 and W2 both. So that's why they are known as the orthonormal basis functions. So this transformation matrix T is a real matrix of two orthonormal basis functions. So now I will show you that how I can use this transformation matrix for having one-dimensional and two-dimensional transforms. So first consider the case of one-dimensional transform. So let's consider your input signal. I mean your time domain signal is 1 and 2, having two elements, and this is my transformation matrix. So as per the definition which we have already seen, that the equation of the forward transform is simply the matrix multiplication of T and X. So that is when you multiply these two values are obtained. So these are your frequency domain values, okay, or transform domain values in general. And to recover X, you will go for inverse transform. So inverse transform is simply X equal to T transpose X. When you multiply these two matrices, you get your signal back. So here you can see a very simple example of forward transform and the inverse transform. Okay. So now let's come to the example of the two-dimensional signal. So just consider one image segment, two-dimensional data. We will use same transformation matrix because it is already 2 by 2 matrix. So by definition, the forward transform is T F T transpose. So this is a T matrix, this is our input signal, and this is a transpose. So when you multiply all these three, I get these values. So these are the transform domain values. To recover my signal back, I need to have the inverse transform. So inverse transform is T transpose F and T. So substituting all these values, okay, so I get my signal back. So this is the example of the two-dimensional transform with this real transformation matrix, okay. We can go for the complex basis functions also. That is also important to show you. Now consider a 3 by 3 complex transformation matrix. So here it is made with the complex orthogonal basis functions. So you can see the complex values here, and as my example is a two-dimensional. Okay, so just consider this matrix, two-dimensional data 1 2 3 4 5 6 7 8 9 3 by 3 matrix. So substituting all these values T F and T transpose, we get these values. Okay, so this is my actually the transform values, which is complex because I have used the complex basis functions. Now inverse transform. So to recover back the signal f, I will use this conjugate transpose of t, f, and then complex conjugate of t. So substituting all the values, I mean these transform values here, I am able to get my signal back. You can see the same matrix I have achieved as the inverse transform. So this is the case where I have shown you the complex basis functions. And now let's see bi-orthogonal transform also. So first we will see the one-dimensional example. In this case, I am considering the 4 by 4 two transformation matrices T1 and T2. As I have already explained, in bi-orthogonal transform, we have to take the two transform matrices, one for decomposition and other for synthesis, I mean the inverse transform. So these are my two real matrices made with the real basis functions. So the forward transform. Okay, so this is my signal actually. This is my time domain signal x 0, 1, 2, 3. Using this equation, T1 is used for forward transform, you can see. So this matrix is used, simply multiplied with the input signal. So I am getting these transform values. So as inverse transform, this will be my inverse transform. Okay, so when I multiply this T2 matrix with these transform values, I get my signal back. Okay, I get my signal back. So this is how the bi-orthogonal transform works. And now let's see some popular transforms like Fourier and other transforms. What are their basis functions, and what is the transformation matrix used for them? So just consider this 8 by 8 transformation matrix which is used for Fourier. You can generate n by n size matrix for Fourier. And how it is generated, for that you have to consider its theory. Okay, that how those basis functions are generated from, which are derived from the basic DFT formulas. So you see that all these first column having the 1, 1, 1, all real values, and then first row having 1, 1, 1, and these are the complex values. Okay, so these values are shown graphically in this figure. Okay, so this is 8 by 8 matrix actually. So the first row is having value 1, 1, 1, all 1. You can see 1, 1, 1, and 1. And similarly, the first column also having the values 1, 1, 1, I mean 1, 1, 1. See, these blue are actually representing the real values, and black is representing the complex values. So 1 is real, and 1 is real, that means 1, and imaginary part is 0, so dot is at this horizontal line 0. Okay, so this is 0 and this is 1. So you can see 1, 0, 1, 0, right? Now see this second value. Second value is 0.707 minus 0.707 I, that means imaginary. So here you can see that this is a 0.707, and this is below the 0 line, so it's the same magnitude, that is minus 0.707. So that is imaginary. Okay, so all real and imaginary values are shown for 8 by 8 transformation matrix. So this T matrix can be used to transform any one-dimensional signal or having 8 sample values, or any two-dimensional signal having 8 by 8, I mean 64 values, maybe an image segment. Okay, so now let's see the same representation of other very popular transforms like this. So here I have shown you the 16 by 16 transformation matrix for the DFT. I have just shown you the 8 by 8, and this is the 16 by 16. So these are all 16 values, and these are all 16 values. So two columns is because these first column is showing the real values, and second column is showing the imaginary values, right? This is for DCT. DCT is not a complex transform, it is a real transform. So you are getting a same column, single column having all the real values, and this is the Walsh-Hadamard transform, and this is the slant transform. And now see the other very popular transforms like Haar transform. It is also having the single column, it's a real transform, and the wavelet Dobischi 4. So all are these basis functions. This is your transformation matrix T. And bi-orthogonal 3.1. So these are the bi-orthogonal wavelets, and here you are you can see that you have the two matrices. Obviously, because bi-orthogonal, as I have already explained you, that the first T1, I mean first transformation matrix, is used for decomposition, and the second one T2 is used for reconstruction, I mean the inverse transform. So these are some graphical view of the transformation matrix of some very popular transform. So I hope that you have enjoyed this lecture, and you have understood the concept that how the transforms are evolved, and how it is very easy to get the transform values by simple matrix multiplications. So please like this video and share this to maximum. So thank you very much for devoting your time. Have a nice time.